Uh, Welcome to the post-lunch session. We have 5 speakers in this session before tea break. Shouvik Datta is the first speaker. Then Aritra Ghosh, Debangshu Mukherjee, Naveen Prabhakar, and Himanshu Parihar. These are the 5 speakers. The first talk is 25 minutes and then 5 minutes question and answer. The remaining 4 talks are 15-minute talks. So without taking much of your time, I now request Shouvik to start. He will talk on operator growth in 2D CFT. So Shouvik, I will remind you after 20 minutes, or you don't need any reminder?
Yeah, you can remind me after 20 minutes.
Okay, after 20 minutes, I will remind you.
Yeah.
Please go ahead.
Okay, thank you, Prasanta. Thank you to the organizers for giving me this opportunity to present my work here. So I'll be talking about operator growth in 2-dimensional conformal field theories, and this talk is going to be based on a paper which appeared recently with the same title, and it was done with 𝗰𝗶𝗶𝗀𝗀 from the University of Warsaw. Okay, so let me begin with some introductory and motivational remarks. So let's start really simple, and let's take a quantum mechanical system and a local operator O, and let's consider the unitary evolution given by the Heisenberg evolution of this operator O. And it's given by this, and as we know very well, you can use the Baker-Campbell-Hausdorff formula, and you can rewrite this as a power series for small times, and you get nested commutators with the Hamiltonian of this operator O. Now, O can be a simple local operator, and the Hamiltonian can have few body interactions. But even if this is the case, the effect of this operator O, if it's a local operator, it spreads out. It spreads throughout the system at later times. So this is this phenomenon of operator growth, and it is a route to understand irreversible macroscopic behavior, how it emerges from the microscopic or quantum mechanical details of the system. And the idea here is that the information or the excitations once stored in simple local operators, it scrambles into a large number of degrees of freedom at later times. Another way to say this is that simple operators grow into ones with higher complexity. So these are just words, but I hope to convince you by the end of the talk that one can make these ideas quantitatively precise. Okay, so just to proceed, let me just introduce some notation. We call this operator as the Liouvillean. This is nothing but the commutator of an operator with the Hamiltonian itself. And we can therefore rewrite this series as this exponential of the Liouvillean acting on this operator O, okay? For instance, this third term over here is like 3 nested commutators. You can write this as L³ acting on O, okay? So that's the Liouvillean. Now, I was saying that operators grow, so let's now try to look at an example just to make this idea very concrete. Let's consider the Ising model. So this is a 1-dimensional Ising model with nearest neighbor interactions. And you turn on magnetic fields along the Ising chain as well as perpendicular to the chain. Okay, so this is a non-integrable model and exhibits chaotic features. And let's ask the question that how does an operator, so this is nothing but a Pauli matrix located at the first site, how does this operator grow with time? So let's look at the terms in this expansion, okay, over here. So for the first term, you can just use the Pauli algebra to evaluate this very easily. You get a sum over 2 terms. If you do it again, you get a sum over 6 terms. And if you do it once again, you get a sum over 13 terms. If you do it even one more time, you get a sum over 41 terms. But the point is that you get increasingly large superpositions of Pauli strings. So for instance, over here, you can look that we started at the first site as a local operator, but over here, when 3 Liouvilleans act on this operator O, you actually get a linear combination of operators that has support over the third site now. So it's the effect of the operator does spread as time progresses. So we need to make this evolution and try to measure this growth. So one concrete way to measure this growth, which we heard about in the first day of this conference, is the out-of-time ordered correlator. So over here, what we do is to take the commutator of the evolved operator along with the probe operator and look at the expectation value of the square of this commutator. And since this becomes a very complicated operator at late times, it fails to commute with simple probe operators. And that fact is reflected by an exponential growth of this expectation value. So by now it's known very well that this growth is characterized by the Lyapunov exponent, which has an upper bound given by the inverse temperature beta over here. So this growth or this measure of operator growth invokes additional probes. However, we would like to quantify the growth without using additional probes. And thereby the hope is that one can extract the truly universal aspects of this phenomenon of operator growth. So the way to do this is one way to do this is something called the Langsos algorithm. So let me introduce this in the first few slides and then mention what physical implications it has. Okay, so it's always good to keep this Ising model example at the back of our minds. And and now I'll be a little bit more general and abstract. Okay, so the Liouvillean evolution, it gives us a set of operators. So we start with some operator and generate more operators by acting the Liouvillean on this operator O. It's nothing but nested commutators acting on the operator. Okay, so pictorially, you start with this operator O, and then at the first step, like L1, L times O, you get 3 operators, for example. Next step, you get even more operators. And in the next step, even more, so on and so forth. What we want to do is to compress this information somehow and see how the growth happens. So that's what we want to do. We want to compress this information. So what we do is to orthonormalize. So we generate new superpositions at each step, but what we do is to orthonormalize with previously generated operators. Okay, so you get an operator O1 by orthonormalizing with respect to O and O2 by orthonormalizing.
You mean Gram-Schmidt, right?
Yes, Gram-Schmidt. Yes, you can exactly that. Yeah, with some particular inner product, which is up to you to choose. Yeah. So that's basically Gram-Schmidt, and so you orthonormalize, and this set of vectors is called Krylov vectors on the Krylov basis. And then you can see that the action of the Liouvillean on one of these Krylov vectors leads to a superposition of 2 other Krylov vectors, the neighboring ones, with some particular coefficients, which are called the Langsos coefficients. For instance, if the Liouvillean acts on O2, it gives a superposition of O1 and O3. Okay, and so by compressing this information, we have this one-dimensional chain. Note that this green dot over here is representative of this complicated superposition over here. Okay, so the further you go along this chain, you encounter more complex operators. So measuring some average position along the chain at some later times gives you an idea of how complex or how complicated your operator is. And that can serve as a measure of operator growth. So I'll be more precise about this in a few slides. So, okay, so we looked at the Liouvillean evolution, got a bunch of operators, orthonormalized it, got the Krylov basis. And by the action of the Liouvillean on one of these operators from this Krylov basis, you can get transition amplitudes, which are nothing but the Langsos coefficients, as I showed in the previous slide. And one can also find what the evolved operator or the evolved state is, and that is given by the action of the Liouvillean on the operator itself. You can re-express this as a linear combination of the Krylov vectors. And the coefficients appearing in this linear combination, these are these wave functions. By some abuse of terminology, it's called, the wave functions, okay? So these encode the probabilities that you reach a particular the nth operator at time t, okay, by taking the mod square of these wave functions. And these Lang's coefficients these wave functions are not unrelated. You can take a time derivative of this equation, and then you can see that it obeys a Schrodinger-like equation, which takes us far. Okay, so this is a bit of formalism, but what is this good for? So this formalism actually provides some bounds on operator growth. So, so the Lang's coefficients, they can actually characterize operator growth. So it can be seen that you can look at the asymptotics of the Lang's coefficients at large n's, which means like far further along this chain. And what happens is that in chaotic theories like the SYK model, it has linear growth. Whereas in integrable models, like some integrable spin chains, it grows as the square root of n. And in free theories, like the Ising model with no magnetic fields turned on, it saturates to a constant. Okay, so this has been seen in a variety of examples. So these observations actually led to this operator growth hypothesis. It was conjectured by these authors. And so the Lang's coefficients, physically speaking, these provide local velocities along this chain for operator spreading. Okay, and the operator growth hypothesis says that in a chaotic quantum system, these Lang's coefficients are just these transition amplitudes while going from one dot to the next dot. These should grow as fast as possible. So the velocities are the fastest in some sense. And so this is the upper bound.
What is the assumption that the Hamiltonian is local and the operator is local?
Yeah, the operator is local. The Hamiltonian has got local interactions, yeah.
Okay, otherwise it can go. If it's non-local, then...
Well, if it's non-local, even then this
will still be, this bound will hold?
Yes. I will just mention that in a minute. Yes. So so this Lang's coefficients, they are upper bounded, like the growth is upper bounded, and it has to be linear. So this has got the same flavor as the Bieber-Bach conjecture, which we heard about on the first day. Even the notation looks very similar, but I don't know whether there is a relation. So the fastest growth is linear, and there's analytic evidence coming in favor of this. So this is related to the question which Suresh just asked. So if you look at the large QSYK model, so in this large QSYK model, you have a Q body interaction. So, and if you look at the large Q regime of it, so this is non-local in some sense, but it's analytically solvable. And the large QSYK model, it actually saturates this. It can be seen that it saturates this upper bound. And there's also mounting numerical evidence in support of this conjecture. And if the Lang's coefficients, they grow maximally like this, if it saturates this, then and this implies an exponential growth of the size of the operator. Okay, so now what do I mean by size? So a measure of operator size is like the average position along this chain. As I said, this green dot is representative of like all these green dots appearing over here. So measuring some average position along this chain gives you a measure of operator size or operator complexity. So if you know the evolved state or the evolved operator, you know this wave functions phi n, which give you the probabilities of being in a particular site along this chain. And from there, you can evaluate the average position by this weighted sum over probabilities. So this is the location, and this is the probability of being in that location. Okay. And as I mentioned, if the Lang's coefficients have linear growth, this quantity called the Krylov complexity, it grows exponentially. Okay, so its exponential grows exponentially fast, far away along this chain to a very complicated operator. Okay, and eventually in today's talk, we'll be interested into the CFTs. So it's good to consider the Lang's algorithm in situations where you have got additional symmetries. So the action of the Liouvillean on the n-1 equilateral vector gives you a linear superposition of neighboring vectors from the next and the previous side over here. And the matrix realization of this Liouvillean just follows from here, that it takes this stripe diagonal or this tri-diagonal form, which is of this. This looks very much like a tight binding model Hamiltonian. So in cases where you have symmetries, like you can have like raising and lowering operators or ladder operators, you can realize the Liouvillean as L plus and a linear combination of L plus and L minus. And the action of L plus on a Krylov vector takes you to the next one, and the action of L minus on a Krylov vector takes you to the previous one. So that's something which can be useful for 2D CFTs. Okay, so now the question I would like to ask is that what happens in 2D CFTs? So we know in 2D CFTs, we have an enlarged or infinite dimensional Virasoro symmetry coming from the modes of the stress tensor. And due to this additional symmetries, there are exact degeneracies coming from the descendants. Okay, so consider a primary operator and let's look at its Fermat module. I mean, there are exact degeneracies at various descendant levels. And we shall be considering irrational holographic CFTs in the stock, so 3 greater than 1. And we roughly have in mind a putative holographic dual in ADS3. These theories should exhibit chaotic features and also should thermalize because we know there are black holes present in ADS3. So one question which I would like to ask here is that how do operators, like simple operators in CFTs like primaries or the stress tensor, how can we analyze the growth of these operators? Okay, so the standard CFT Hamiltonian is given by the 0 modes of the stress tensor, and it's given by this, so this is well known. However, primaries and quasi-primaries, these are eigenstates of this above Hamiltonian, and therefore the time evolution is trivial. It just gives an overall phase, okay? So what we do here is to make matters more interesting. We pick a different evolution or a different way to drive the system or quenching the system via a unitary protocol, okay? So this is a different Hamiltonian, if you like. This is made out of the linear combination of L1 and L minus 1.
I have a question.
Yeah.
So you're saying that quasi-primaries are eigenstates of the Hamiltonian, but what about the secondaries and the others? They are not eigenstates, right?
Sorry, what do you mean by secondaries?
The others, what do you mean by quasi-primaries? What are the other sorts of operators?
Yeah, I mean, all descendants are eigenstates of the Hamiltonian.
Descendants, yeah.
So I mean, we always think of the Hilbert space of CFTs, and whatever states appear over there, they are eigenstates of the Hamiltonian. So
what I'm saying is if you start with the descendants, then maybe you could still generate such a thing, right?
Yeah, descendants are also eigenstates of the Hamiltonian. I think there is no confusion here. We can discuss this later on. So maybe I should proceed. So we pick a different evolution or a quench protocol, which is made out of the linear combination of L1 and L minus 1, which is this. And this choice is not ad hoc. Like we heard about adding inhomogeneities in CFTs in the first day. And you can realize this Hamiltonian by adding inhomogeneities. And there's also an interpretation of this as the evolution by the modular Hamiltonian, as was shown by these authors. Okay, so we have this unitary, and the action of this unitary on this primary, on a primary state is just given by this. And you can expand this exponential, and it's, as you can convince yourself, it's just going to be a superposition of descendants of the primary's Fermat module. Okay, so that's what it's going to be. So you might think that, okay, so this is like just various powers of L minus 1 acting on this primary operator. However, these states for example, n-1 with various powers, these have got non-zero overlaps with actual Virasoro descendants. So these are the elements that actually appear at the corners of your CAX matrix. And the very fact that your CAX matrix has got off-diagonal elements means that the usual Virasoro basis which we work with, this is not an orthonormal basis. Okay, so for instance, this is an overlap of two level 2 descendants in the Virasoro basis, and which has got non-zero overlaps. So they are not orthonormal. So we need to find an orthogonal basis or an orthonormal basis in order to track the evolution more carefully. So thereby we can build the Krylov vectors, as I was mentioning previously. So one can build an orthogonal basis by using what is called the oscillator basis or the oscillator formalism. So the Virasoro algebra and its generators can admit a differential operator realization in terms of an infinite collection of oscillator variables. So this is very much like the simple harmonic oscillator, in which you can realize the oscillator algebra in this way, and which is realized through this differential operator and this variable like this. And the Virasoro generators, they can be realized in terms of an infinite collection of these oscillator variables. So the details don't matter, but one can construct an orthogonal basis using this formalism.
Sorry, Shouvik, you asked me to remind you after 20 minutes, so
okay.
I just...
Thank you. Yeah. Okay, so once this orthonormal descendants are constructed, these are essentially given by monomials of these oscillator variables, suitably normalized. And there's a one-to-one correspondence between this orthonormal descendants to integer partitions. So these are raised to various powers. And if you calculate the L0 eigenvalue of that, you can find the descendant level to be an integer, and each of these states, they have a one-to-one correspondence with integer partitions. And there's also a one-to-one correspondence of integer partitions to Young diagrams. So just to illustrate this, let's look at level 3 descendants. So in terms of oscillator monomials, they can be realized as U1 cubed, which corresponds to the partition 1 plus 1 plus 1, and it corresponds to the Young diagram given by a single column over here. And 3 can be written as 1 plus 2, which corresponds to this Young diagram and this oscillator monomial. And 3 can, of course, be written as 3, which is given by this Young diagram and this oscillator monomial. So one important thing here is that we are working with irrational CFTs, and in order for this correspondence to work, there should be no null states, and there aren't any null states in irrational CFTs, so we can proceed with this. Okay, so let's see how the Lang's algorithm works in 2D CFTs. So as I said, the evolution is given by this. And what we need to find is the action of L1, L-1 on specific descendant states, because these are orthonormalized descendant states. Now we can realize these descendants as Young diagrams, and the action of L-1 adds a box. So a box can be added to this in 3 ways. And the action of L1, it removes a box, and that can be done to this Young diagram in these 2 ways. So that's shown over here. Actually, this action of L1 and L-1 is a part of a bigger picture, which is called the Young's lattice. So the idea here is that you start with a primary, which is like descendant level 0. You add 1 box, you go to descendant level 1. You add another box to this box, you go to descendant level 2, so on and so forth. So the Young's lattice is a graph or a lattice with Young diagrams at its vertices. And the edges or links or bonds of this lattice, they correspond to the addition or the removal of 1 single box. And in order to relate these things to the Lang's algorithm, the weights associated to the vertices correspond to the wave functions of the evolved state. And the weights associated to the edges, they correspond to the Lang's coefficients, which is given by this. So just to contrast this with the usual non-degenerate case, we had a single one-dimensional Krylov chain, but that generalizes to this degenerate Fermat module because we have exact degeneracies, and there is no way to compress this information. Okay, so the Young's lattice provides a generalization of this Krylov chain into the CFTs. So one can actually evaluate what the Lang's coefficients are using the oscillator formalism. And the Liouvillean matrix, it takes this tri-block diagonal form. So each block connects to nearby descendant levels, like this over here. And there is a further reduction because only the non-zero contributions comes from nearest neighbors of this Young's lattice, and that is shown over here. And the standard non-degenerate case, recall that that took this simple tri-diagonal form, and the generalization of that is this tri-block diagonal form over here. Okay, so the weights of these edges are given by the Lang's coefficients. This is something which we can evaluate analytically using this oscillator formalism. So let's look at this. So if we proceed along this path, along the Young's lattice, the leftmost one, so this is just a single row diagrams. We can evaluate this analytically. And if you take the large n limit of this, you find linear growth. Similarly, if you go along this rightmost edge, you find a square root n growth. And actually, you can evaluate the Lang's coefficients between any two descendant states. For example, between two typical states as well, you can evaluate what it is. But the essential point over here is that you do get linear growth along the leftmost edge of this lattice. And you can plot it numerically, and it shows linear growth over here. So the fastest growth can be found on the leftmost edge of this lattice, and this saturates the conjectured upper bound on the growth of the Lang's coefficients, which is this. So we can track the evolution further by evaluating the evolved state or the evolved operator very explicitly. And that is going to be a linear combination of descendants of this operator O, since it's a primary. So it's going to be a descendants of this primary O. And we can get these wave functions very explicitly. And from there, we can calculate the probabilities of reaching a particular descendant state at time t. So it's given by the mod square of these wave functions. And it depends on the specific details of the integer partition, and it's given by this. So what do these probabilities encode? So it encodes the information about the chances of reaching a specific descendant state at time t. So the picture in terms of the Young's lattice is as follows. So at t is equal to 0, the probability is peaked at the primary state. And then as time progresses, this probability actually spreads out into higher level descendants. Okay, so operator growth under this protocol into the CFTs, it can be realized then as spreading into this bath of descendants of the primary's own Fermat module. So that's how it happens. One can actually plot these probabilities. So the probabilities of the probability of remaining in the primary state, it actually decreases exponentially with time. One can also find this through the autocorrelation function. So this is measuring the overlap of the evolved wave function with the original state, and that decays exponentially. And at late times, what we see is that it becomes a superposition of very high level descendants. That's what we see over here. One can use these probabilities to find the average layer of the Young's lattice reached at time t, or the average descendant level reached at time t. So that's encoded through the Krylov complexity, and it's given by this. And this quantity shows an exponential growth. So we see that this primary operator, it grows exponentially into a complex operator. So it's a complex high-level descendant. And this result is universal, and it applies to all C>1 CFTs with 0-0 symmetry. So I realize that my time is up. So let me just take 1 more minute, if that's okay.
Yeah.
Sorry. So just to conclude, we saw that operator growth into the CFTs can be realized as spreading along the Young's lattice. And we also found the saturation of the conjectured upper bound on the Lanczos coefficients. And we could evaluate the probabilities of reaching a specific descendant state at time t. And the Krylov complexity, as expected, it showed exponential growth. So there's a laundry list of extensions which one can think about. So I considered a single operator, but one can think like, what if we have more than one operator or like operator products? One can ask like, what happens in minimal models? I considered irrational CFTs over here, or CFTs with higher spin conserved currents, symmetric orbifolds, or the half BPS sector of n = 4 super Yang-Mills. Now, this might look like a very odd list of topics, but if you forget about the first two examples, in all these cases above, the states or operators do admit a Young diagram-like description. So it would be nice to see whether the picture of the Young's lattice can also be applied to study operator growth in these settings. So that's all I have to say. Thanks for your attention. Yeah, and I'm sorry for going over time.
Thank you, Shouvik. So we have several questions. Somadat, please go ahead.
So time evolution can take place only through the Hamiltonian, right? So I don't understand how you can have a
So this is a deformation of the Hamiltonian. So usually the Hamiltonian, you can write it as some integral of the stress tensor. Now you can put a specific envelope function in front of the stress tensor, which is like adding some inhomogeneity, which is going to lead to this operator, which I showed you. It's going to be L1 plus L minus 1. Yet another way to think about this is that, okay, you're not exactly doing time evolution, but you can use the Baker-Campbell-Hausdorff formula to decompose the unitary, which I wrote down as a combination of translations, special cut form 1 translations, and dilatations. And you're studying operator growth under that. So yeah, so that's a perfectly physically well-defined evolution. Yeah.
So Aninda?
Hi, Shouvik. Thanks for a very nice talk. I had a question regarding the calculation of the Lanczos coefficients. So when you calculate the Lanczos coefficients, you have to implicitly or explicitly choose a norm. So were you using the Frobenius product?
Yeah. So over here, the oscillator basis provides you with a specific norm, which is just a simple norm between two descendant states, and that's what I was using.
And would this conjectured growth of Bn be sensitive to the norm?
I think not. I think there has been like studies like with using the thermofield double norm, for example. And even in that case, I mean, this is within the limits of this conjecture. Yeah. So I think there has been different norms studied as well. Yeah.
Okay, thanks.
So Ravi?
Hi, Shouvik. I have two questions. So first is related to what Somadat already asked, but can you take the perturbation to be something proportional to L0? And what happens in that case?
So as I said, like, I mean, if you take a primary operator and if you add L0 on it, it essentially just gives you the conformal dimension, right?
Right.
So it's not something which is
interesting,
non-trivial. Yeah.
Okay.
So it just gives you a phase. That's all. So yeah. So in order to like make it more interesting, one can study evolution under other unitaries. I mean, this is like choosing, I mean, in the quantum information parlance, if you like, I mean, this is like choosing a specific quantum circuit, which is built out of a unitary operator.
Okay, and so in the derivation, is there anywhere that you restricted to? So basically, I suppose your derivation is completely, it does not depend on the specifics of the 2D CFT in the sense that whether it's vacuum or finite temperature or torus CFT.
Yes. So yeah, that's a very good question. So the only thing which I assumed is a C greater than 1 irrational CFT. That was the only assumption over here.
Okay.
And this result applies for that. Now, you could study like operator products instead of one single operator. That would give you more details about the OP coefficients and the spectrum of the theory. But for the setting which I considered over here, I mean, I don't need any other assumptions. Yeah.
Okay. Thanks.
Okay. Before we go to Sunil, we have hands raised up to Loga. Any new hand raise will not be permitted in the interest of time. So Sunil, please.
Yeah, Shouvik, very nice talk. Can you just mentioned to Surabhi that this result is where your results are valid for C greater than 1 irrational CFTs.
Right,
but
right.
where did you actually use the fact that they are irrational?
Yes, so that was used when I used this correspondence of descendants to integer partitions and then to Young diagrams. So if you have got null states, which is, for example, in rational theories, there will be a reduction in each descendant level, and then this corresponds.
But you're looking at Virasoro descendants, right?
Yeah, it's Virasoro descendants, but
so for C greater than 1, there are no Virasoro null states, but there are still rational CFTs.
Yes, but this is irrational. That's what
I'm asking. Where did you use that? You're saying that you use the fact that there are no null states, but even though there are no null states of Virasoro algebra, you still have irrational CFTs.
Yeah, so that's
sorry, you still have rational CFTs.
Yeah, so if you have rational CFTs, then there will be null states, right?
Not of the Virasoro algebra.
Yeah. Okay, yes. Okay, very good. So over here, I restricted to the case that my symmetry algebra is just Virasoro.
So you assume that there's no extended chiral symmetry?
Yes.
Okay.
So that was important. Yes, thanks for the question. So no additional conserved currents, no double algebras, no supersymmetry. Yeah.
No Kac-Moody currents in particular, which are quite generic. Okay, thanks.
Yeah. I should have emphasized that. Yes. Yeah.
Argue?
Yeah. Hi, Shouvik. Thanks for the good talk. So the operator growth that you are showing on the Young lattice, that reminds of this Planck growth, right? So in that growth, normally we have a limit shape kind of thing where if you go to large n, then you have a particular representative or particular Young diagram which dominates.
Yes.
So is there something happening here? Is there any dominant thing in the large box limit or something?
Yeah. So that's shown over here. Like I showed the typical states. So in the large n limit, I mean, it goes to a limiting shape, and then you can evaluate what the Lang's coefficients are like between two typical diagrams or two typical descendant states, and that turns out to be this. I mean, there are also some interesting combinatorics, which you're also familiar with, like with Vershik and Kerov and Logan and Chep.
Yeah, that's why
those combinatorics actually enter and they provide some bounds on the norms of these operators. Yeah, you can find details in our paper. Yeah.
Oh, sure. Thanks.
Yeah.
Pratik?
Hi, Shouvik. So my question is regarding the asymptotically growth of this Lang's coefficient. From which range of n you are taking this asymptotics? Because after the large n, this bn should come down to 0, right? Because we are going to the end of the Krylov space. So
yes. So what you just said is true for a finite dimensional quantum system. It's not true for an infinite dimensional quantum system like a quantum field theory. You're right, like this, that this Krylov complexity exponentially grows and then it saturates. And that fact is true only for finite dimensional quantum systems, not like something like a CFT. So these keeps growing, and it keeps growing forever.
Okay, so even in a finite dimensional system, so from which n you can call this Lang's, I mean this.
That's not something which is. I can't give you like a number for it. Yeah, but it's large enough. Yeah.
Yeah. Okay. Thanks.
Buddhaditya?
Yeah. Hi, Shouvik. Thanks for the wonderful talk. My question was regarding the different growth of Lang's coefficients that you see for different directions in which you go along the Virasoro algebra, the Varma model. So what is the explanation for that? Why is it different?
Yeah, so if you look at the Lang's coefficients in detail, I mean, these actually depend on the specifics of the descendant state, actually. So it depends on the integer partition, the details of the integer partition. So that's the reason why you see different numbers for it. For instance, over here, you see I've labeled the Lang's coefficients like between two specific Young diagrams. So there is a very fine-tuned dependence on the details of the integer partition. So that's why it's different,
Okay, I see. So it's sort of like it's chaotic along one path and
yes,
integrable along the other things.
Yes, something of that kind. Yes.
Okay, thank you.
So last question by Logan.
Hello, Shouvik.
Hi, Logan.
Nice talk. So I wanted to ask just two questions. One question is, you had chosen a particular kind of evolution with L1 and L-1.
Yes, yes.
Can I do this with other Virasoro generators and so on?
Yeah. So sure. I mean, as long as it is unitary, you can do it. I mean, you can choose LK, L-K. And yes, this can be done. Like, I mean, then you don't go between nearby layers of the Young's lattice, but you jump across K layers one at a time. Yeah, but it can be done. It can be calculated using.
And you think the results will be similar?
Yes, the results will be similar, but this K dependence is going to enter. Yes, actually for like SL2R, like you can take like LK, L-K and L0 and like massage the generators a bit, and this also forms an SL2R algebra. And like the K dependence enters in some way, but the form of the results, they essentially remain the same. Yeah.
Okay. So just one more question, and since you were talking about this in terms of Young tableaus and so on, yes, do you think there is a way to think about this in terms of some matrix model or some fermions and so on? This particular evolution model?
Yes, there are a lot of similarities, but yes, I don't know. Yes, I mean, very similar things arise in that case as well. Yeah, but I don't know at least like how to make some precise connection at this stage. Yeah.
Okay. Yeah. Okay. Thanks, Shouvik, for very nice talk, and I'm sorry for not taking any more questions. So Shouvik, please stop sharing. Now we have Aritra.